Good morning, everyone, and welcome to the first video in a series that will hopefully allow us to finish off Math 252. So you'll recall last time we were working on finding the following inverse Laplace transform, and the Laplace transform we were looking at is the transform of a complicated fraction, which we found we needed partial fractions for. So we had worked out the first part of the partial fraction decomposition. We worked it out that it was a over s squared plus, a over s plus b over s squared plus cs plus d over s squared plus 1. I'm going to scroll down here to where we ended up. We had written out, we'd multiplied by the common denominator and then started to put in various values for s in order to find the constants a, b, c, and d. By letting s equals 0, we found that our constant b was 6. And then by putting s is equal to I, we found that c was 0 and d is 6. And then finally, in order to find out what a is, we can let s equal 1, or any other convenient value. This value doesn't make any term 0, but is easy to calculate. I'm just writing that down here. And if we do that, then plugging into the left-hand side, we get that 18 is equal to 2a plus 2b plus c plus d is equal to 2a plus 12 plus 0 plus 6. And that means that 18 is equal to 2a plus 18, and that therefore a is equal to 0. And so what we can conclude from that is that our partial fractions give us that 12s squared plus 6 over s squared onto s squared plus 1 is equal to 6 over s squared plus 6 over s squared plus 1, because we found that a is equal to 0, and we also found that c was equal to 0. Alternatively, if you're not a fan of the complex number part, a different method would be to, let's just draw a little box here. Alternatively, apparently I can't spell alternatively today. Alternatively, you could take your original statement after you've multiplied the common denominator, get to 12s squared plus 6 is equal to as onto s squared plus 1 plus b onto s squared plus 1 plus cs, let's move this over a bit, cs plus d onto s squared. And you can actually multiply out the right-hand side, and then, being kind of obvious here, but the left-hand side is 0s cubed plus 12s squared plus 0s plus 6 is equal to, and then you get a pile of terms on the right-hand side. You're going to get as cubed plus as plus bs squared plus b plus cs cubed plus ds squared, and the right-hand side, if you collect like terms, becomes a plus c onto s cubed plus b plus d onto s squared plus as plus b. And then if you do some matching of coefficients, notice the 0 here on the s cubed becomes the same as a plus c. Similarly, you can take the 12 on the s squared term, and that's going to be b plus d, and you get the following system. You get that a plus c is equal to 12, b plus d is, a plus c is equal to 0, b plus d is equal to 12, a is equal to 0, and b equals 6 for the same result. Okay, so where does that get us? What we do know is that the Laplace transform there, then, of 12s squared plus 6 over s squared onto s squared plus 1 is equal to the inverse Laplace transform. Did I say inverse Laplace transform last time? I can't tell. It's equal to 6 over s squared plus 6 over s squared plus 1 is equal to, and honestly, if you're comfortable, you can just write down the final answer, but let's do the extra step. It's 6 onto the inverse Laplace transform of 1 over s squared, which is the same as 1 factorial, plus 6 onto the inverse Laplace transform of 1 over s squared plus 1. And that just gives us, using the Laplace transforms table, 6t plus 6 sine t. And that's it.